we could only fit about 1,000 transistors on a chip. Hence, the processor of this little calculator took 2 chips. One for arithmetic, one for control and timing. And that was on one bus. Not 4 bits, not 8 bits, not 16 bits. 1 bit. Little bus wires running. But it didn't have to be super fast and work. Now, a lot of people think back to Hewlett-Packard calculators. What would you say about the early ones that you really remember about them? RPM, I heard it. RPM, right? RPM. Oh man, RPM is something computer scientists learn. Our calculators are powerful. They can calculate more powerful equations than all the other little people who talk about parentheses and arithmetic formulas, and this is real power stuff. Well, it turns out that actually it was RPM because there wasn't enough space in the ROMs. The ROM memories could only hold about 500 bytes. And 3 of them ran the entire HP35. There wasn't enough room to parse the equations the way humans write them with parentheses and convert them into the order to do things. So have you hit a button? 6. Put a 6 in a display. Push another button. 7. Put the 7 in place. Plus, add them together. And it was easy because you were using your brain to order everything and tell it what order exactly to do the operations. But that was the real reason we had RPM. Well, when Texas Instruments came out with their calculator, it was a big learning experience. We laughed and pulled out our card with a huge equation, like one of those statistics equations that can take you 20 minutes to calculate the answer by hand. And we laughed because this Texas Instruments calculator could never do it since it had parentheses, and parentheses made it a toy. The same way a Macintosh would be a toy because it had pictures. I thought I was the smartest one there, and I said, okay, I'll try the equation. I looked at this equation, I looked at the TI calculator. I'm starting to think, okay, the first part that you solve is this innermost part. I did everything I did with HP calculators. Oh, but to get there, I'm going to have a bunch of parentheses levels, 6, or do I put 7? And then I realized I'm never going to remember how many parentheses levels I'm at as I work my way through this complicated equation. It isn't humanly possible to do it on the Texas Instruments calculator. But then I told myself, wait a minute, the truth tells me it is possible. They wouldn't put out a calculator that couldn't do it. So there has to be a way. What am I missing? Clear out your mind. This is really good a lot of times in engineering. Clear out your mind of the way the world is today. What else would there be? And what came in my head was type it in from left to right, the way it's written. So I typed it in from left to right as fast as I could go. I had to guess whether square root was prefix or postfix, before or after the data. And to type so fast I might get a digit wrong. I got the right answer the first time. This equation was so hard, nobody ever got it right the first time on an HP calculator even. And I showed it to the other engineers. I told them, hold it. Now I said, type it in from left to right. Everything that's on that card, type it in what's on the left first. Not one of them could do it. It's very hard to give up your established, learned skills. You learn how to solve a problem. You have to think, what do I do first? You're ordering, you're making your brain do the work. But technology is supposed to make us forget about using our brain. It's supposed to relieve us of all that. So, while working at HP, I still love electronics. I had no chance to ever meet a girlfriend or getting married. So when I came home from work, more fun electronics projects after I watched Star Trek and ate a TV dinner. And I'm so proud of this, I started the first dial-a-joke in the San Francisco Bay Area. Started it in my Cupertino apartment. Why was I first? Because in 1971, let me get the year straight, 1972, there was only one phone company, a monopoly. You could not legally purchase, own, or use your own telephone. You could not legally in the United States purchase, own, or use your own answering machine for a dial-a-joke. So I had to pay a huge amount of money to lease the only one they had. Huge amount of money for a young engineer. But I believed in humor so much, I did it. And I told Polish jokes. And the Polish American Congress Incorporated didn't like it, so I said, what if I changed it to Italian jokes? They said, fine. This was all before political correctness. A lot has changed in just our lives, if you think about it. A lot of the way the world works. That's probably a more significant change as political correctness than computers and the internet are. No, I'm just kidding. I saw Pong in a bowling alley. And okay, so I went to build Pong, and I was into the sort of chips that were all a certain style of chip that really Fairchild was behind. The synchronous series, 74, 174 little 4-bit shift registers, the 166 adders or whatever they were, and I liked using those. And for Pong, I actually built about just 28 chips, 28 little TTL chips, $1 chips, running Pong on my home TV, which was cute. But then I got this idea, if I missed the ball, it'd be funny if it spelled a 4-letter word. Like darn. So I said, well, we got these proms at work, these little programmable things to develop our calculator code on. I'll program up a couple of proms to have words in them, the bits of the words. And it took 2 proms to have 256 bytes of memory. 2 separate chips in those days. That's how few chips were, parts were around. That's how expensive memory was. Went over to another division, I programmed up my words and worked. So then it came time to do breakout. Breakout needed another type of memory. It needed memory to remember roughly 128 different bricks that were there or they weren't there. The ball hits a brick, poof, the brick disappears. So I got a 256 by 1 RAM, a standard RAM. So that was an easy decision. That one I didn't have to, there's no magic about it, nothing special. And then came the ARPANET. And I discovered the ARPANET, and I said, oh my God, I have to have one of these. Well, the only way I can have something is if I build it myself, and I built it so I could type on a terminal to a computer in Boston. A computer in Boston could talk to my TV set by putting little 1s and 0s on the screen in the right place to add up to letters. And that was great. But as I designed things, I was really into designing things at absolute simplest, minimal, lowest cost any human could do. I always forced myself to try to think of things that other people wouldn't think of that were smart. And I chose for the memory of all the characters on the screen, roughly 1,024 characters. For that memory, I searched and searched magazines, the bad ones, and found a little PMOS chip, very sensitive to static. It was PMOS instead of NMOS. Little chip with only 8 pins that had 1,024 bits of memory. Perfect. These little tiny, tiny chips. The lowest space, the fewest pins to connect, always made the smallest design in my mind. So the biggest decision I made in most of the projects of my life was what kind of memory to use that's the exact right, smallest, simplest, and more importantly, the cheapest there is. And I achieved it in that case. These were dynamic RAMs. As I worked at Hewlett-Packard on our calculator chips, I learned that when you build in a little bit of memory, it costs a bunch of logic to store a register. But if you make it dynamic, it only has to hold the data until it gets clocked and sent down the stream to the next thing. Hold it for a brief period of time, a 2,000th of a second, set it on. Hold it for a 2,000th, set it on. These were the smallest little 1 transistor bit cells, the smallest you could do on silicon. And I always kept that in my mind. If you could ever design anything, my approach was on silicon. If you can have a shift register, shift it in, and then shift it around, rotate it around into itself, hold it for a while, hold it for a 2,000th of a second, shift it around back into itself, all the ones right back down the tree, you get a bunch of glitches on the lines. But if those glitches are tolerable, that is the best solution. In other words, always keep in your mind what are the don't care situations, and also what are the don't matter or can't happen input conditions. I got really good at just doing all that in my head all the time. So now I heard about these things called microprocessors. They were starting to come to our attention. And I had a terminal that I could talk to faraway computers. So I said, let's just put a microprocessor and some memory right here. Well, I had built a computer 5 years before, the cream soda computer. I built a little computer where you flip switches and punch buttons and get 1s and 0s into memory. I wanted a real computer now. It was the one I dreamed of when I told my dad I'd have a computer someday. He said it costs as much as a house. I said I'd live in an apartment. And the 4K Nova, but you had to have 4K of RAM to have a programming language. So I had to have a microprocessor and 4K of RAM. And that summer, the summer of '75, 3 companies, AMI, I think MOSTEC or TI, and Intel, came out with 4K bit dynamic RAMs. The first time ever RAM was cheaper than core memory. Oh, I loved having to avoid all the entanglements of core memory. So I bought 8 of these chips from AMI. and a guy was selling them in our club. 22-pin devices, hooked them up. I got my dynamic memory working and refreshing and all that, and it actually worked great. And Steve Jobs, came along and he said, well, why don't you use Intel chips? I said, well, I looked at them all. The Intel ones are the best ones, but I could never afford anything from Intel. They're just way overpriced. And he said, well, what if I can get you some for free? You got 18 chips, 16 chips for free. I would always be too shy, too embarrassed to ask for things for free. So luckily, the Intel chip turned out to be the forerunner of all of today's dynamic RAM. It was the way they implemented it. So it was a very lucky choice to put it in this little first computer. And the computer was built, and then Steve Jobs had ideas of how we could sell it and make money, and we started Apple Computer. Now, I hadn't designed that product as a computer. I let the memory that was available, the price of the memory, the efficiency of the design, which components I chose, define how fast that computer could work. And it turns out that because of these shift registers that I chose, the dynamic shift registers, I could only change a byte on the screen 60 times a second. Every time the screen refreshed, I could type in a new character, enter a new character at the right point. I had to wait until the whole screen shifted around all its characters and stick it in the right one. 60 characters a second. That was great for going over a modem to the ARPANET. Modems were only 30 characters a second anyway. So it was an optimized design. But now, in the age of the microprocessor, a microprocessor can do a million things a second. You need much faster. You need to be able to update anything on the screen instantly. And that led to this idea of, I was working on it in my head. Why don't I use the exact same memory, the dynamic memory that the microprocessor talks to? Why don't I make a part of that come out and get put on the screen all the time? What an easy solution it was. I mean, it might seem easy now, but when you're doing it, it's just not the way it was ever done before. It was a huge advantage. So the Apple II was really designed to